Welcome to episode 2 of Everything You Need to Know About JPEG. Last episode, we did an overview of the process of JPEG compression, going from raw pixel data into the compressed bit stream that ends up in a JPEG file. Now we will be focusing on decoding a JPEG file that is already compressed. Last episode, we talked about 3 things that we know we will have to read from the JPEG file. That is the quantization tables, the Huffman tables, and the Huffman coded bit stream. Those are the 3 that we mentioned. There are a couple others that we will discover. But in this episode, we will read each of these things out of a JPEG file that we will be testing with, store all of this information, and at the end, print it all out to the terminal, and that way we can verify the correctness of our program. First things first, how do we know what to read next out of a JPEG file? JPEG files use what are called markers. These are 2-byte values that indicate, based on their value, the type of data that is coming next. For every marker, the first byte is always FF, and the second byte is the value you actually use to know what kind of data you're about to read. So you may be able to guess at this point that there is a marker indicating the definition of a quantization table, the definition of a Huffman table, or the start of the Huffman coded bit stream. But starting simpler, there is a marker called the start of image marker. The value for the start of image marker is D8, and for short, we refer to this as the SOI marker. Now, it is a strict rule of the JPEG format that every JPEG file must start with the SOI marker. So the way we're going to do this is talk about one kind of marker in our drawing slides here, then switch over to code and implement the reading of that kind of marker, switch back to drawing, talk about the next marker, and go back and forth like this, keeping our focus on just one kind of marker at a time. So with that, let's hop over to our code for the very first time and get going with a program that verifies that our JPEG files start with the start of image marker. So let's take a look at what we're starting with. We have pretty much a blank slate. For now, we have a single header file where we will put a whole bunch of constants and struct definitions. And we have a single CPP file called decoder that will include our constants, a main function that will take a list of JPEG files as arguments, and inside of main, we will process every JPEG file one at a time. I also have a very simple make file, just to make compiling slightly easier. I'm running on Linux, so I'm using G++, but the code we're going to be writing should be very portable, so you should be able to compile with any decent modern C++ compiler. You're going to need to be using at least the C++ 11 standard, but I'm pretty sure it would work just fine with newer versions as well, such as C++ 14 and 17, but this will do. So when we type make, it will compile our source file and output the executable in the bin folder. But that's just a picky detail, so let's actually get started. First things first, I'm going to define 2 type defs that will come in handy a bunch. The first of which is an unsigned char, so we have a quick way to refer to a byte. Since we'll be dealing with individual bytes a lot, it's better to have this. The one thing that is annoying about doing this is every time we try to print a byte, it will really try printing a char because that's what the variable will actually be. So we'll have to do some unfortunate typecasting, but only when we print bytes. Anyway, that's not that big of a deal. Next, I'm going to paste in a bunch of constants for the markers that we have not talked about yet. So we will get to these throughout this episode, but here you can see the first one we've talked about, the start of image marker, which, as I mentioned, is D8. As I said, we're going to process every command line argument as a JPEG file. So first, to do that, let's verify that we were given some arguments. And include IOStream, of course. Since the first argument is always the name of the program that is running, there will always be at least one argument, but we need to print an error if there are not at least two. And then we can return. Otherwise, we want to process every argument except for the first one as a JPEG file. Store the file name as a constant string. And now at this point, we need to be thinking about data structures. All of the markers at the start of the JPEG file that give you the quantization tables, the Huffman tables, etc., can be thought of as the header of the file. So let's make a struct called header, where we will store everything that we read. This struct we will fill out as we go, but for now let's write a function that takes a file name and returns the header that is constructed by reading the file. All right. Take in that file name by constant reference. You'll see I will be trying to use constant references everywhere that I possibly can. They make code very clean and beautiful. Let's start by opening the file, including file stream. Opening the file as input and binary, because we don't want the file stream to default to text-based input. Also, let's try to stay focused on robustness, clean, proper error handling. So if the input file is not open, print an appropriate error message. And return. Now we can make the header. Personally, I like allocating things with new by using the standard no throw. In this case, it's not really going to make a big difference. Hypothetically, if this allocation were to fail, we would have to catch a bad alloc exception, or don't catch the exception and let a program crash. Personally, I prefer using standard no throw. What standard no throw does on failure is returns null pointer. I personally find that to be much more elegant and allows us to handle the error ourselves without try catch blocks. We simply check if header is a null pointer. And if this is the case, close the file and return. Now we can begin reading from the file. Now, because markers are always 2 bytes long, we will start by reading 2 bytes at a time. So we read 2 bytes, and if either of them are not what they're supposed to be, if last is not FF or current is not start of image, where this start of image comes from our header file equal to D8, then this file is not a valid JPEG file. Let's add a flag to our header struct, indicating if it is valid or not. We can default to true and set this flag to false if we ever encounter something illegal in the file. So in this case, when the first 2 bytes are not FF start of image, set the header's valid flag to false. Close the input file and return the invalid header. And at this point, of course, we can return the header as well. So now our read JPEG function correctly handles the first marker. In main, after calling read JPEG, if header is null, there's nothing to do. We can just continue on to the next input file. Otherwise, if the header is invalid, print this out to the console. Delete the header, and continue. Here is the point where we would actually process the Huffman encoded bit stream. And then we can delete the header. All right, this seems like a pretty good start. Let's try it out. Run the make file. Run the decoder. And let's take a look here. Here is a JPEG that we will be testing with. Nice picture of a cat. The file name is cat.jpg. And our program finished without complaining. Let's try running it on a different file. We have our make file here right next to it. If we tried passing it the make file, it should fail because the first 2 bytes are not FF start of image. And you can see it prints invalid JPEG. So that's a good sign. In the case of the start of image, there is no data following the marker, but most of the time there will be. In this case, the FFD8 marker will be immediately followed by another marker. Now, in some ways, the order that the markers will appear is pretty flexible. There are some ways that it's not flexible, which we will talk about. But at least in the case of our cat JPEG test file, the marker that comes immediately after the start of image marker is called an APPN marker. There are actually 16 APP markers, where the second byte is in between E0 and EF. APP stands for application, and what it means is it's a place to put application-specific data. So if the JPEG was encoded in Photoshop, Photoshop might put some of its own information inside an APPN marker. What you will see most often is that the file will contain the APP0 marker, which is almost always used as the JFIF marker. The JFIF format is a limited version of the JPEG format, essentially restricts you to fewer options, which makes it easier for encoders and decoders to support all possible options. As it turns out, the enormous majority of JPEG files are actually JFIF files. This doesn't really matter that much to us, and all of the data contained inside of the APP0 JFIF marker is data that we can ignore. But if we're going to ignore it, we have to read through it regardless. So like I said, some markers, like the start of image for example, don't have any data following the marker, and some do, like the APPN markers. For the markers that do have data, after the marker, the next 2 bytes are an unsigned 16-bit integer representing the size in bytes of the data for this marker, and that includes the length bytes. So if this value were 8, you read these 2 bytes and learn that this marker is followed by 8 bytes of data. You need to read 6 more bytes. You will always subtract 2, because just to figure out what the length is, you already read 2 bytes. Most of the time, we care about this data, but in the case of APPN, we don't. So we read the bytes just to advance forward in the file. So back in our read JPEG function, after we verify that the first 2 bytes are the start of image marker, we will continue processing markers in a loop until we reach the end of the file. Our while condition is actually going to be while the header is still valid. I should also mention just like the start of image marker, there is an end of image marker that likewise must be the last 2 bytes of the file. So in this loop, we can watch for the end of image marker to detect when we should break from the loop. So every go around in this while loop, we will be processing the next marker. Before the start of the loop, let's prepare our last and current bytes again. At the beginning of this loop every time, check if we've reached past the end of the file, which you can do with this not in file syntax. For the file stream objects, the not operator is overloaded to return true if any of the error flags inside the file stream are set, such as if you've read past the end of the file. If this is the case, we got to the end of the file without coming across an end of image marker. So print an error accordingly. Set the valid flag to false. Close the input file. And return the header. Now it's going to happen a lot where we detect an error, so we print a message, set the valid to false, close the file, and return the header. So from now on, I'm going to skip past every time I have to repeat these same 4 lines with a more specific error message. It's possible we could design some more elaborate way to handle errors, but this is sufficient, albeit a little bit redundant. But I'm not going to waste any more time talking about these lines every time we have to type them. Now remember, at the beginning of this loop, we expect a marker every time. So if last is not equal to FF, that's a problem because that means we are not looking at a marker. Now we are ready to process the marker. In our constants file, we have 16 APPN marker constants whose values are all between E0 and EF, like we talked about. So in our marker loop, we will check if current is in between APP0 and APP15 inclusive. And if so, read the APPN marker passing the input file and the header. This is going to be the pattern that we will follow for all kinds of markers. Make a function whose sole responsibility is to read one kind of marker. We will give it the input file to read from and the header to store information into. Since we don't care about the data inside the APPN markers, the function for reading them is pretty easy. We'll always be passing the input file by reference, and every time we pass our header pointer, we will pass it as a const pointer. This still allows us to change the data inside the header struct. This const just makes it so that we can't cause the pointer to point to anything else. For fun, let's print a little message letting us know what kind of markers we're reading. And like I said earlier, we need to read the next 2 bytes, representing a 16-bit unsigned integer, which is the length of the data in this marker. To do this, we will read a byte from the file and shift it left by 8 bits and read another byte out of the file and add them together. Every time in a JPEG file when we read a 2-byte number, they will always be in big endian, meaning we left shift the first byte that we read and add to it the second byte, as opposed to little endian, which would be the opposite, where you read the first byte and then shift the second byte left by 8 bits and then add the 2 together. Now we also know the length value includes the 2 bytes that we just read. So we read up to length -2 bytes. And since we don't care about the data, we can simply say infile.get, and this discards the result. This might seem pointless, but it really is important because we need to advance our position in the input file so that when this loop is finished, the next thing we will read using a .get is the next marker. All right, back here again. After processing the current marker in our while loop, before looping, we need to get last and current to read the next FF and the next marker. Now, just so our program doesn't behave erratically, let's break after processing the APPN marker so that we return the header after reading just the first two markers, the start of image and the APPN. Here again, we can make, typo on my part, of course. Here, we do not want to redeclare last and current, just update its value. All right, it worked that time. Run the decoder on cat, and we see that we are successfully reading the APPN marker. Now, I kind of want to apologize that it's probably been rather boring so far. But now we're finally ready to do the exciting part. The next marker that we run into using our cat example is the marker for defining quantization tables. The quantization table definition marker is called DQT, which stands for define quantization tables. The marker for it is FFDB, followed by the length of the marker data, followed by a single byte giving us some info about the table. This byte contains two pieces of information, one of which is the upper nibble of the byte, and the other is the lower nibble of the byte. The upper nibble is a 0 or a 1, basically a Boolean value, and this tells us if the quantization table values are defined as 8-bit values or 16-bit values. This has some important implications. If the quantization table values are 8-bit, we just read a single byte for every value in the table. And if they're 16 bits, we read 2 bytes, shifting the first byte over and adding them together, like we've been doing with the length. But to be honest, I have never once encountered a JPEG file that uses 16-bit quantization tables. Every JPEG file I've ever looked at uses 8-bit values. So we will code for it anyway. We will allow 16-bit quantization tables because the JPEG standard says that they are allowed, but we don't have to worry about it or think about it that much. The lower nibble of this table info byte should have the value 0 through 3. And this is the table ID. In episode 1, we mentioned that the luminance channel has a separate quantization table from the chrominance channels, so that implies there will already be at least 2 quantization tables, but the standard allows for a maximum of 4. However, most of the time, you will only ever see 2 quantization tables being used in a JPEG file, IDs 0 and 1. So again, we're going to allow for all 4 quantization tables, including ID 2 and 3, but you will only ever really encounter JPEG files that use quantization tables 0 and 1. After this table info byte, there will be either 64 bytes, if this is an 8-bit quantization table, or 128 bytes if it's a 16-bit quantization table. And these are the table values. Now, this is what it would look like for the definition of a single quantization table. But there is some freedom in how the JPEG file is allowed to define multiple quantization tables. Assuming we're just going to be talking about 8-bit quantization tables, this length value can equal 2 plus 1 plus 64, in which case you read the marker, the length, which equals 67, the table info, and then the 64 bytes as the table values. Then you read the next marker. Or this marker could define more than one quantization table, and this length would reflect that. If this marker defines 2 quantization tables with IDs 0 and 1, this length would be 2 plus 1 plus 64 for the first table, plus another 1 plus another 64 for the second table. That would be this value. So you have to repeat these 2 steps until you've accounted for this entire length. If this length was 67 and there was only 1 quantization table defined, the JPEG file could still use more than 1 quantization table. It just means that there will have to be more than 1 FFDB marker. So that's something to keep in mind. The number of FFDB markers you encounter does not necessarily equal the number of quantization tables that this file uses. But with that, let's go ahead and try coding this in our decoder. Let's take care of that right here. if current equals dqt. Then we will read the quantization table. We need a function for that. Print our little message saying we're reading a defined quantization table marker. Read the length the exact same way. And this time, instead of a for loop that runs exactly length minus 2 times, we will repeat while length is greater than 0, because we don't know how many quantization tables we're about to read. After reading the length, we can subtract 2 right away. And as we talked about, we read a 1 byte value, which is the table info. Every time we do a infile.get, we can subtract 1 from the length. From the table info, we can extract the table ID, which is the lower nibble of the table info. We can get the lower nibble by binary ANDing the table info with 0f. The table ID must be between 0 and 3. It's unsigned, so it's already guaranteed to not be less than 0. But we need to check if table ID is greater than 3. This time in our error message, we can give more helpful information by printing the invalid table ID that we encountered. As I mentioned earlier, this is an instance where we need to cast the byte to an unsigned int, because a byte is actually a char, and we don't want to print characters in cases like this. And just return. Once we find something like a nonsense table ID, there is no point in continuing. So we need a struct to hold a quantization table. Luckily, it's not that complicated. All a quantization table is going to have is a property called table, which is an array of length 64, and we will give this array an initializer of all zeros. I mentioned in episode 1 that we will be referring to the 8x8 matrix as a one-dimensional array of size 64. The reason is this is actually more flexible. For example, if I wanted to loop through every position, now I can use a single iterator that goes from 0 to 63, as opposed to a 2D array that is 8x8. To iterate over every value, you would need a nested for loop, and sometimes that's what you want anyway. But with a 2D array like this, a single for loop isn't really an option. The reason I say a one-dimensional array is more flexible is because you can still use a nested for loop. You don't have to use a single for loop. Just to demonstrate this real quick, we know we can use a single for loop that goes from 0 to 63 and refer to the table at index I. And this is what we cannot do with a two-dimensional array. But if we wanted to iterate over the rows and the columns, we can still do that using a y and an x coordinate like you'd expect for a two-dimensional array. And then the trick is you give the y coordinate times the width, which is 8, plus the x coordinate. If we were using a two-dimensional array of 8x8, we would get row y, column x as the x and y coordinates. But we can accomplish the same thing when we have a one-dimensional array. We just have to multiply our y coordinate by the width and add our x coordinate. Anyway, I don't want to waste too much time with that, but it is kind of important because many times we will traverse 2D arrays using both methods. One index that goes from 0 to 63, and using two indices, both going from 0 to 7. Now in our header, we will store a quantization table array, give it a max size of 4, even though, like I said, we will mostly only ever use the first 2 quantization tables in this array. And I'm using a static array because it doesn't waste much space to create all 4 quantization tables every time, even if we only use 2 of them, rather than doing something like a dynamically sized array. That would just add more complexity to our code and not give us any real benefits. However, since the quantization tables will always exist, it will be kind of nice to know whether or not a particular table has been initialized. So we'll add a Boolean to our table called set and default it to false. And anytime we populate a quantization table, we will set its set flag to true. Now that we have guaranteed our quantization table ID is valid, we can set the quantization table's set flag to true. Now we need to actually read the values that we put into the table. And they might be 8 bits, they might be 16 bits. If table info, if it's upper nibble, and to get its upper nibble, you can shift the 8-bit value to the right by 4 bits. If the upper nibble is non-zero, then this is a 16-bit quantization table. So for all 64 quantization values, the quantization table we are reading, its table at position I will equal the next 2 bytes from the file, just like this. Once we read the table, we can subtract 128 from the length. Otherwise, we do pretty much the same thing, except we don't read 2 bytes from the file, we only read 1. And we subtract 64 from the length instead of 128. Now, one problem with this, you might have noticed I like using unsigned ints everywhere that it is applicable, instead of just using signed ints without thinking about it. And usually that's a good thing. In this case, though, that turns out to be a problem, because our condition is while an unsigned int is greater than 0, which will always be true unless it's exactly 0. So this is a potential hole in our program. If our program is reading an invalid JPEG, one of these subtractions from the length could cause the length to go below 0, but because it's unsigned, we'll make it a very large number. And this will continue to be true and will continue to loop, and we don't want to do that. So most of the time, length will be an unsigned int, but in this case, we want to be able to know if it goes below 0 to detect for errors. So we need to make it signed in this case. For things like the APPN markers, unsigned is fine, because there's no chance of it underflowing. Anyway, when this loop breaks, length is either 0 or negative. If it's not 0, meaning length is now negative, we don't know exactly what went wrong, but the original length we read didn't match up with the sizes of the tables we read. So we can't say much else besides saying that the marker is invalid. And that's it for reading quantization tables. Back in our main, let's print our header to be able to read everything stored inside of it, which at this time is only the quantization tables. So we'll put that in right here. This time, our header pointer can be a constant pointer to a constant header struct, because reading it or printing it doesn't need to modify the pointer or the data that it points to. Quick check if the header is null, return. We'll have a section where we print the quantization tables for all 4 of the quantization tables. If quantization table I is set, print the table ID and print the table data. That will just look like this for all 64 values. Print the value in the table, and every 8, print a new line so we get a nice 8x8 grid of values. And that's it. Now let's run this on cat again. Make and run it, and it didn't print anything. That's because in our marker loop, we have a break after reading the APPN. Let's move that to after reading the quantization table, and try again. Now, would you look at that? cat.jpg, we read the APPN marker, the DQT marker, then we print the tables that were read in the DQT marker. Table 0 has these 64 values, and Table 1 has these 64 values. If you recall from episode 1, we said that the chrominance channels are quantized more heavily than the luminance channels, and that is because our eyes are much more sensitive to subtle changes in brightness or luminance than they are to subtle changes in color or chrominance. So JPEG files can get away with throwing away much more chrominance data while having almost no impact on how we perceive the image, while not getting rid of nearly as much luminance data, because that would have a bigger impact on our perception of the image. And here you can see that reflected. This table 0 is the luminance table for this image, and you see much smaller numbers, especially towards the top left of the table, versus table 1. Most of the values across the whole quantization table are a lot bigger than in the table for luminance. Oh yeah, one more thing about how the quantization table is defined. The 64 values are not laid out in the file from left to right, top to bottom in the table. So again, here's an 8x8 matrix with positions labeled from 0 to 63, left to right, top to bottom. Now our loop that reads the quantization values from the file uses the looping variable I, which goes from 0 to 63. However, we don't want to store the quantization value at position I, because that would store the first value in position 0, then position 1, then position 2, and so on. But because the quantization values are stored in the order of the zigzag traversal, we want to store the first value in position 0, the second value in position 1, the third value in position 8, 16, 9, 2, and so on. Now, this doesn't change the fact that I goes from 0 to 63, incrementing by 1 every time. So instead, we need a list of these indices in this order. So let's write that out real quick. If these were in a list that is 64 long, then the index of the first value is at 0, 1, 2, 3, and so on, which turns out to work great because this is like I in our loop. So when I equals 0, we store the quantization value that we read in position 0. When I is 1, we store it at position 1. When I is 2, we store the quantization value in position 8. So this solves the problem of I counting forward from 0 to 63, while the quantization table is stored in the JPEG file in zigzag order. So let's fix that in our read quantization table function. Let's add that list that we just talked about of the indices in zigzag order into our constants file called zigzag map. And you can see, as we talked about, it starts with 0, 1, 8, 16, 9, etc. Then we can index into this array using I to retrieve the correct index into the quantization table. That's a very easy change over here. Instead of the table at position I, we go into the table at position I of the zigzag map. And do that again here as well, of course. And now we are truly finished with reading quantization tables. If we were to run this again, we can see the quantization table is being printed in the correct order this time. Now it looks much more clear that the upper left corner has smaller values than the bottom right corner, whereas our first time printing it, all the small values were along the top. That's of course as a result of us storing into the table in the wrong order. I apologize, I feel like my terminal font has been a little bit small, so I increased it a little bit. I'll try to remember to keep it like this. Here's the G++ command if that's a little bit clearer. And here are our two quantization tables. Also, it might help to validate some of this information by looking at cat.jpg in a hex viewer. So at the top of the file, it starts with FFD8, which is the start of image marker, followed by FFE0, which is the APP0 marker, the JFIF data that we're ignoring, and that marker is followed by the length of the JFIF data, which is hexadecimal 10 bytes long, or 16 in decimal, and that includes the length bytes. So we skip 16 bytes. Then the next marker is FFDB, which is the definition of quantization tables, followed by the length 84 hexadecimal, which is this many bytes. After the length is the table info for the first quantization table, 00, where the upper nibble means it's an 8-bit quantization table, and the lower nibble means it's table ID 0, followed by 64 bytes, which are the quantization values. This 28 is the last quantization value for that table. The next byte is the table info for the second quantization table. Upper nibble, again, means it's an 8-bit quantization table, and the lower nibble means it's table ID 1, followed by 64 quantization values. And this is as far as we have read into this file so far. A little bit of foreshadowing, the next marker we're going to talk about is FFC0. The next marker we're going to talk about is the start of frame marker. The marker for the start of frame is FFCX. For the start of frame, the marker can range from C0 to CF, but it excludes C4, C8, and CC, which are 3 unrelated markers. So that's a little bit confusing. With those 3 exceptions, there are 13 different start of frame markers. I've mentioned we will be focusing on baseline JPEGs, which use the frame marker C0. The only other very common frame marker is the progressive frame, which we will be going over in a future episode, but the other 11 start of frame markers are used so rarely that I've never seen one, so we will probably not go over the other 11. We will only cover baseline and progressive, but for now, only baseline, which is C0. What it means for a JPEG to be a baseline JPEG is that there is only one Huffman-coded bitstream in the file, and that one Huffman-coded bitstream contains all the information you need for every MCU. When we get to progressive, we will learn that that means there can be many bit streams that pass through all MCUs many times. As you can imagine, that's a lot more complicated. With baseline, it's easy and straightforward. Now, the start of frame marker also contains more information than just the type of encoding. Again, we read the length, which is 2 bytes. Then we read the precision, which is 1 byte, which tells you how many bits are used for each of the color channels. Strangely enough, this value must be 8. Meaning that the Y, CB, and CR, and consequently the R, the G, and the B, must be 8-bit values ranging from 0 to 255. There is no other option. JPEGs don't support higher or lower precision color data. Then we read the height and the width. Both are 16-bit values, and both must be non-zero. The next byte is the number of components, which are the same thing as channels. They're called components and channels interchangeably. This is allowed to be 1 or 3. If it's 3, then it is a Y, CB, CR JPEG, like we've talked about. And if the number of components is just 1, then it is a grayscale JPEG, and the only color channel in the file is luminance. A grayscale JPEG has luminance data, or brightness data, and no color data. It is also possible to see a JPEG with 4 colored channels, but that would be a CMYK JPEG, which is a color mode we are not going to support, at least right now. So we will stick to 1 color channel and 3 color channel JPEG files. After reading the number of components, which should be 1 or 3, you will loop 1 or 3 times, reading data about each color channel. The first byte you read is the component ID, which should be 1, 2, or 3. The next byte is the sampling factor. We will have an episode much later on about supporting different sampling factors, but for now, we will only support files that use a sampling factor of 1, so don't worry about what that means yet. And then the third byte is the quantization table ID used on this component. Usually, component 1 is luminance, which gets quantization table 0, and components 2 and 3, the chrominance channels, get assigned quantization table 1. But it doesn't have to be that way. This is defined in the start of frame marker. Also worth noting that the start of frame marker must be present in the file, and there must be only one start of frame marker. If you are reading a JPEG file and get to the Huffman-coded bitstream without ever encountering a start of frame marker, that is no good because you don't know the sampling factor, you don't know which quantization tables to apply, you don't even know the number of channels or components in the Huffman-coded bitstream. Also, if you encounter a second start of frame marker after already reading one, that is also no good because the first start of frame marker told you the mode and the dimensions, so you can't run into this information twice because it can't change. Alright, let's implement reading the start of frame marker. First, let's make some updates to our header struct. Let's store the frame type, which in our case for now is going to be baseline. Let's store the height and the width. And let's store the number of components. Let's also make another struct for our color component information. What we read is the sampling factor which is separated into horizontal and vertical. Again, this isn't that important, and we will default to 1 because that is all we're going to support. And the last thing we read was the quantization table ID. Let's also store an array of color components of size 3 in our header. And since we're using a static array similar to the quantization table, let's keep a flag in the color component indicating whether or not this color component is used in the JPEG image. And that should be all we need. Back in our marker reading loop, if current is equal to start of frame 0, our header's frame type is start of frame 0, and we need to read the start of frame marker. Now let's add in our read start of frame function right here. Print that we are reading the start of frame. We need to make sure we don't read more than one start of frame marker. So if the number of components is already not 0, then that means we've encountered more than one start of frame marker. Then we read the length like normal. Then we read the precision. If the precision is not 8, we have an invalid JPEG. Then we read the height. Then we read the width. If the height or the width is 0, we have an invalid JPEG. Then we read the number of components. If the number of components is 4, we have an unsupported CMYK JPEG. If the number of components is 0, that's obviously a problem. Now we can loop for the number of components. The first byte to read is the component ID. This error checking is a little bit of overkill, but there is another color mode that we haven't mentioned called YIQ, and color channels I and Q get component IDs 4 and 5. Of course, we're not going to be supporting those. This is not something we can detect based on the number of components because YIQ JPEGs also have 3 color components. Now, I mentioned that the color component IDs for Y, CB, and CR are 1, 2, and 3, instead of what you might assume, 0, 1, and 2. So in fact, component ID 0 is invalid, as well as component IDs greater than 3. Now we know that we have a valid color component ID. Let's get a pointer to the color component that we're reading from the header. That way we don't have to read into the header's color components array over and over. Now the index into this array is component ID -1, because component ID is 1, 2, or 3, and the index we need to use needs to be 0, 1, or 2. Now some more kind of extreme error checking. If this component from the header is already used, that means this component ID that we just read ended up being the same value more than once in this same loop, and that should certainly never happen. If that wasn't the case, we can set the component's used flag to true. Now we need to read the sampling factor. Now I haven't mentioned it yet because I'm not trying to focus on it, but the sampling factor is broken up into its upper nibble and its lower nibble, which are the horizontal sampling factor and the vertical sampling factor. So like before, we get the upper nibble by shifting to the right 4 bits, and we get the lower nibble by ANDing with 0f. And last but not least, the component's quantization table ID is the next byte in the file. And while we're here, we should verify that the quantization table ID assigned to this component is not greater than 3. Now that seems kind of verbose because we have a lot of errors we can check for. But once we read this data for every color component, that should be the end of this marker. However, we should still check that the length we read at the start was correct. That would be minus the 8 bytes we read at the start, the precision, the dimensions, the number of components, etc. Also minus 3 bytes for every color channel. And if that is not 0, then again the length that we read didn't line up with the number of bytes that we ended up reading based on the number of components. And that is reading the whole start of frame marker for baseline JPEGs. Back in our marker reading loop, let's move the break again so that we break after reading the start of frame marker instead of the quantization table. And let's update our print header function to print information that we learned through the start of frame. For the start of frame, we can print the frame type, which should be C0 in our case, then print the dimensions, the height and the width, and then for the color components, print the ID, which is I+1, print the horizontal and vertical sampling factors, which should both be 1, and print the quantization table ID assigned to this color component. And this reminds me, before we run this, we need to add a check against the sampling factors so that if they are not 1, we say that it is unsupported and set it to invalid, but this is going to be a temporary check that we will remove once we do support horizontal and vertical sampling factors. So let's add that right here. If the horizontal sampling factor is not 1, or the vertical sampling factor is not 1, then abort. Okay, let's try running this again on cat. Now we are reading the start of frame marker also, printing the quantization tables. We can see that the frame type is C0. These are the dimensions of the cat. For the color components, ID1 has sampling factors of 1 and 1 and uses quantization table ID 0. And both components 2 and 3 use quantization table 1. Okay, this episode is getting pretty lengthy, so I'm going to stop it here. I'm going to turn this into a 2-part episode. We are about halfway done with the markers that we have to read. So in part 2, we will finish up the JPEG file reading by reading the remaining markers. I know this episode was a long one, so thanks for sticking through. Please like and subscribe if you are enjoying this series, and I will see you again in episode 2, part 2.